GJ1214b is an exoplanet 48 light years away orbiting the star Gliese 1214 in the constellation Ophiuchus. This exoplanet in particular is unlike any other we've seen before. With a mass 8 times that of the Earth's, but with only a third of its density, scientists suspect that a large fraction of the planet's mass is water. Enshrouded beneath its thick, steamy atmosphere lies a boundless and seemingly bottomless global ocean as far as the eye can see, and possibly one that extends all the way down to the planet's core. So, how deep are these oceans exactly? Well, to answer that question, we will need to make a set of assumptions. The planet has a radius of about 17,000 kilometers and an atmosphere of unknown thickness, so let's assume it to be twice that of the Earth's, or about 900 kilometers. The average density of the planet is 1,870 kilograms per cubic meter, whereas that of the Earth is 5,500 and that of water is 1,000. So when you do the math, we could solve for the mass fraction of the planet that's rock, or 19.33%, which leaves over 80% of the planet's mass to be water. For reference, only 0.05% of the Earth's mass is water, and using the volume formula 4/3 pi r cubed, we could then find the total depth until the rocky core by finding the core's radius, which comes out to be 6,100 kilometers. And when you subtract the planet's total radius of 17,000 minus the thickness of the atmosphere and the core, we determined that the oceans are 10,000 kilometers deep. The exoplanet has a mean temperature of about 200 degrees Celsius, and if the density of its atmosphere is similar to that of the Earth's, the pressure at its surface is 2 atmospheres. Its gravity is only 91% of that of the Earth's, and using the relationship P is equal to P atmosphere plus rho gh, we could find the pressures at any depth in the ocean of the planet. As we will soon see, it's really interesting to see what happens to this ocean water when we increase the pressure enough. At the temperatures and pressures we normally encounter on Earth, water is usually at its liquid state until it reaches its boiling point of 100 degrees Celsius. This is not quite the case in GG1214b, where the immense pressures can keep the water liquid even when it's well above its boiling point. From the graph, we could see that once we travel deep enough into the planet's atmosphere, we would eventually reach its ocean's liquid surface. The deeper we go, however, we will soon find that this water undergoes further changes due to the increasing pressures. At about 560 kilometers beneath the surface, the liquid water eventually compresses into exotic high-pressure ice, first Ice 7. Another 5,000 kilometers down, this Ice 7 becomes Ice 10, another high-pressure ice. Towards the bottom of the ocean, pressures are nearly 1 million atmospheric pressures. Using P equals P atmosphere plus rho gh in conjunction with this graph, a MATLAB simulation was used to determine these depths. While we know a lot about terrestrial planets and gas giants, not much is known about this new class of water worlds like GJ1214b, whose masses are mostly from water, unlike the Earth, and so there is a knowledge gap. These calculations can be a first step in addressing this, giving us a better glimpse at how these oceans in these worlds can vastly differ from our own. This knowledge can also help us when we explore and settle on other planets or moons in the future. For example, Europa has been suspected to be a habitable moon in our solar system with a possible ocean hundreds of kilometers deep beneath its icy exterior. And this knowledge on water worlds can, for example, help us better prepare to explore that moon's oceans.